So this lecture, we're going to look at different pipe systems, hooking pipes together of different diameters and lengths. So if several pipes have different diameters and lengths, they're all connected together. They can form what's known as a pipe system. If the pipes are connected in succession, we refer to that as being in series. And if the pipes are connected as follows, we consider that to be pipes in parallel. So this is similar to current flow. It's exactly the same kind of situation. So the analysis of pipe in series is similar to that used to analyze a single pipe. In this case, however, in order to satisfy the continuity equation, the flow through each pipe segment must be the same. So for this three-pipe system, the Q values have to be the same in each one. Also, the total head loss for the system is just equal to the head loss of each segment, plus all the minor head losses exactly the same. So therefore, the energy equation between, let's say, A and B in this situation, it just follows the same pattern as before, except here the head loss term is equal to the major head losses in each of the lengths of pipe, plus all the minor losses. So for pipes in parallel, it's a similar analysis is used. In this case, the flow, before the branch has to equal the flow after the branch. So QA equals QB, and so here Q1 plus Q2 has to equal the sum of those. So again, this is equivalent to current flow into a junction, right? The current end of the junction has to equal the current total sum of the currents out of the junction. So here, if you apply the energy equation from A to B, you get a similar result here, but here, in this case, the head loss 1 has to equal the head loss 2 because it's in parallel. And again, this is similar to voltage, right? So the voltage loss, if this was a current flow here and a current flow there, the voltage drop here and the voltage drop there would have to be the same. So let's look at example 10.9. Here we have pipes BD and DE are made of galvanized iron and have diameters of 6 inches and 3 inches respectively. So for B has a diameter of 6 inches, and so B to D is 6 inches, and D to E is 3 inches. So let's say we have a gate valve at E is fully open. Determine the initial discharge of water at E in gallons per minute. It has a filter at C that has a KL value of 0.7. He says neglect the loss within the reducer at D and take the kinematic viscosity to be the value shown. So here we can, there's many approaches to here. I think the easiest is probably to apply the continuity equation first. And again, up here at A, the velocity is approximately 0. We've seen that multiple times for a big reservoir or big bucket of water. If the average velocity throughout the larger pipe is V, and through the smaller pipe is V prime, then we can apply the continuity equation as follows and calculate that V prime is equal to 4V. Next, we can use the energy equation between A and E. So here again, we write down the energy equation, and we got our head loss terms that we have to look at. So the pressure at A, that's 0. The velocity at A is 0. Our reference level is going to be at E. So you have 3 feet, 4 feet, and 6 feet. So that makes 13 feet. Z at A is 0. And I'm sorry, not Z. Z of A is the 13 feet we calculated. H of the pump, there is no pump, so that part's 0. The pressure at E is 0 since it pumps out the atmospheric. The velocity at E, we're going to use the value we just calculated, at 4 times V, 2G. Z is 0 here because we're at the reference level. There's no turbines. So the only unknown is HL. and V. So we get an equation involving HL, and V. The second part now, let's calculate the head losses in the pipe. So the major head losses are given by the Darcy-Wabash equation, as we talked about before. The minor losses are due to the several different situations. So here at B, we have what's known as a flush entrance. So you can look back on the previous lecture slides, and it's 0.5 times V squared over 2G. It's got a elbow, 90-degree elbow, so that's 0.9 V squared over 2G. It's got the filter, so we were told that's 0.7 times V squared over 2G. And it's got a fully open gate valve, so that's 0.19 V squared over 2G. So all of these values, you'll have to be given tables on an exam to look these values up. You just kind of have to pay attention to the wording of the problem and look and find the appropriate valve or entrance. So we can calculate the total head loss, the major head losses, plus all the minor head losses. Here F and F prime are the friction factors for the large and small diameter pipes, because we have different pipe diameters here. So if you plug, so we don't know those terms yet. So if you plug those values in, you get the following equation. So now we have the two equations we found. This equation, we found that equation. So we can substitute the H of L value for up here and write a single equation. And we can solve this for V. It's a function of F and F prime. So now we want to use the Moody diagram to calculate the relative roughness and the Reynolds numbers for the two pipes. So for the small pipe, we calculate the relative roughness of 0.001. And for the for the large pipe, for the small pipe, it's 0.002. Somewhere we can calculate the Reynolds numbers. The only thing we don't know is V, right? But so we can't directly use the Moody diagram to get V. So in this case, we have to use a trial and error approach. So if we assume intermediate values of F as 0.021 and F prime is 0.024, and again, how do you get those values? Well, it's just trial and error. And so our book, he just picks two values that he knows sort of work. It takes a lot more work than this to actually figure these out, but he's just showing the example of kind of a complicated example of how to solve this. So he's guessing these values for F and F prime. So using the values of F and F prime, we can calculate the velocity and the Reynolds numbers now. Now, once you calculate these values, you can go back to the Moody diagram to check the results to see if that comes out and is consistent. So, and when you do that, you actually find that yeah, these actually give these values. So it was a pretty good guess. However, if you got different results, you'd have to go back and make new guesses for F and F prime and continue that until you got the same F and F prime that you had guessed. So this is a rather complicated example. It is a real world example in a way, but it does take time to go back, because if you guess wrong for these initial values, it's going to take a while before you're actually able to figure this out. So finally, we can calculate the flow rate Q, and then we can calculate this discharge rate in gallons per minute. We can convert this value here to gallons per minute.